This one is 2.26. Here we have a water pipe which is made of these wooden staves which are held together by these wires that are drawn on this figure here, and this steel bar has a diameter of 2 centimeter. There is an internal pressure here which is 50 Newton per centimeter square. Because of safety and to avoid leakage, the maximum allowable increase in the diameter of these bars is 0.1 centimeter. So delta D max is 0.1 centimeter. We need to estimate the maximum allowable longitudinal spacing S between the circumferential rods. So if I consider two rods from this here, this is the space S that we are looking for. Now this is very similar to your example 2.7, and in that problem also we analyzed only one half of this axisymmetric body. So if I look at one half of this body, there is this steel bar that is sitting outside, and inside we have this wooden staves that are there. Now as an assumption, what we are going to take here is that these wooden blocks that are there, and they are just held together by this rod, so they will not be transferring any tangential load, meaning they cannot do load transfer in this direction. Only thing that they can do is the radial load transfer or the radial deformation. So because of pressure, internally we have this pressure acting here. To balance this pressure force on this steel rod, there will be this tangential force Ft on this side, and due to symmetry, same force is going to be on the other side. Now if I do the force balance for this, and this is coming from your example 2.7, 2 times Ft is going to be the projected force due to this pressure in the vertical direction. And if I consider this distance here, this is 80 centimeter. So your pressure value times 80 centimeter. Now this whole thing is considering the gap between two of these wires. This distance is S right here, right? So the area on which the pressure is going to be acting will come from this S also. So the projected area is going to be 80 times S. From this you can see your Ft value, if I substitute the value of P there, is 2000 S, where S is again written in terms of centimeters. This we need to keep in mind. S is in centimeters. Now let's look at the wire and its extension. So if I take that wire and flatten it out, on this side here and this side here we have this force Ft, this force Ft. The length of this wire, because we are considering only one half, is going to be pi times the diameter, okay, divided by 2, because pi d is going to be the overall perimeter, so this is going to be only half of that. Now for the wire, if you look at the diameter here, this inner diameter here is 80 centimeter. After that we have this 5 centimeter from the wood, so 80 plus 5 on two sides, so 10 centimeter comes from the wood, and the diameter for the wire is, diameter for this bar is 2 centimeter. So if we are going only up to the center, so it's going to be 2. So this is going to be the mean diameter for this. So this is 92 centimeter dia for steel bar, okay. This is the length, and if I look at the cross section here from the side, your cross section is defined by this 2 centimeter diameter. So cross section A in this case is going to be pi d square over 4, where your d is 2 centimeters divided by 4. So this is basically pi centimeter square. Now since it is made of steel, we are going to take the elastic modulus as 205 gigapascals. So now if I look at the extension in this rod, it's going to be Ft force. Length for this is going to be pi d divided by 2, okay, where d value we have already calculated, which is 92 centimeters here, divided by elastic modulus, which is 205 gigapascals, and this times cross section area, which is pi centimeter square. Now this is the deformation in this wire, and which is happening for half the perimeter. Now if you consider this half rod that we have, and your delta D max is given as 0.1 centimeter, this will change the perimeter for this half circle by pi into 0.1 centimeter divided by 2. So basically this is 0.05 pi centimeters. So the allowable delta is 0.05 pi centimeter, which is equals to ft. Ft is 2000 s times pi d over 2, where d is 92 centimeters, so this becomes 46 pi divided by 205 gigapascals times pi centimeter square. So in this equation everything is known except for this s value here, and when I solve for this s, this comes very close to 35 centimeters.